Hello everyone, in this video we're going to talk about binary search trees. Here you see an example of the binary search tree, and I'm going to talk about and define what is a binary search tree. So first of all, binary search tree is a binary tree. And we learned that the tree is a kind of data structure in which we have the root, which is a node, and the root is connected to connected to other nodes through some path or some edges. So here the node with the value 10 is the root, and all other nodes, as you see, are somehow connected to the root through some paths or edges in between or in the paths. So why we call it a binary search tree, and what's the difference between binary search tree and just a regular binary tree? The binary search tree has two specific features, which is the left child of any node is smaller than its parent, and the right child of a node is greater than or larger than its parent. So if you look at node 10 with the value 9, you see that it's the parent of 7, and because 7 is left child, it has higher value compared to its left child. And also 9 is the right child of 5, which means that it should have a higher value, and it is correct here. So we see that it pattern repeats. So every children and also the grandchildren of 10, on the left side it is less than 10, and every child on the right side of the 10 is greater than 10. So that's a pattern that repeats for every subtree of the binary search tree, and we're going to see that how the search operation works and how the insertion works in the binary search trees in here. So we're going to start with the search operation first, which is finding a node in the tree that we have. The good thing about the binary search tree is that based on the rules of the trees, of the binary search trees, we expect to find the node that we're looking for in the faster time, although it's not the case all the time, but usually that's the reason that we are creating the binary search trees, to being able to do the search operation faster than linear search. So let's say that we are searching for value k equal to 14 in this binary search tree that we see here. So what's going to happen? We're going to start with the very first node, which is the root, which is going to be 10. So we're going to compare k, which is 14, versus 10. And because k has a higher value compared to number 10, which it means that the value k cannot be on the left side of the tree, because based on the binary search tree, every child on the left side of the node is smaller than that. So automatically we can just prune a lot of the unnecessary searches, or skip that many searches. So because k is greater than 10, we need to go to the right side of the 10, node 10, which is 15. So now we're gonna, so that's the first search that we have. The second search is comparing k versus or with 15. This time k is 14, so k is 14 and number versus number 15, we know that it is smaller. So that means that we should not search the right side of the 15, and we need to go to the left. So that's the third search. We're going to compare k with the left child of 15, which is 13. So here k is greater than 13, and we need to search the right child of 13, which is number 14. So the fourth search will be k versus 14, and there's a match and they are equal to each other, so we're good, and we can return the data at node 14, or where the number 14 exists. So here, how many search we did? We did only 4 searches, and among like the these many like the nodes that we have. So we have 13. We have 11 nodes. We have 11 nodes, and we only had to search 4 nodes in order to find number 14. Although again, it's not all the case, and as you see here, the tree that we see here is almost a balanced tree, and we're gonna see that what do we mean with like the balanced tree. So here, balanced tree means that a balanced binary tree means a tree that the difference between the height of the left subtree of a node and its right and the height of its right subtree is either 0 or 1. So here we have almost a balanced tree. All nodes are expanding or the tree is expanding in a very balanced shape. So, but this is the very easy to see that. It's very easy to see that we can actually end up with searching all nodes. So here's an example of a tree that we can actually do more than one search, or we need to search the entire like the tree. For example, this tree here that we have 5, we have 8, and we have 15, and we have 20, and let's say we have 25 here. So let's say we're searching for k equal to 25. So for instance, for finding the k equal to 25, we need to compare with 5, with 8, with 15, with 20, and with 25. So we need to do 5 searches to find a number 25. But actually, if we had the trees like this, so we had number 15 as the root, and then we had maybe number 5, and then here we had number 8, and then here we had number 25, and here we had number 20. So that's another binary search tree with the same numbers. And here to find k equal to 25, we only need to do 2 searches. First with k equal to 15, comparing k with 15, and the second one is comparing k with 25, which is the answer, or is the match. So the performance of a binary search highly depends on how the binary search tree is structured. So that's why there exists a lot of like kind of the trees that trying to keep the balance or trying to keep the binary search tree balance, such as Abel trees or red-black trees. You can just watch my other videos about these also kind of trees. So if we want to talk about the time complexity, as you see, it highly depends on the height of the like the tree. So in general, we can say that in the worst case, the time complexity of the binary search in a binary search tree is from the big of h, and h is the height of the tree, or the distance from the root to the depth of or to the node which is at the deepest part of the tree. In these examples, nodes 18, 14, 7, and 1 are the nodes that are furthest from the root. So the height of the tree in this example is 4. So that means that at the worst case, we need to do at least 4 searches. So for k equal to 14, that was a successful search. For sure, we might end up with some unsuccessful searches. For example, if we're looking for number 19, or let's change the name of the variable to, for example, z. For z is equal to 19. What's going to happen here? We have 10, so it's going to be one comparison with 10 because 19 is greater than 10. So we need to go to the right child of 10. So 19 is greater than 15, so we need to go to the right child of 15. 19 is less than 20, so we need to go to the left, and we need to go to the right side of the 18, but it does not exist, so it is an unsuccessful search, and we did 4 comparisons. So that's two examples of like the successful searches and unsuccessful searches, and also talking about like the balance factor of a tree, although I'm going to talk about the balance factors in another video in more details. Now let's take a look at the implementation of a binary search tree. The code that I'm using here, again, almost as a Java code, very similar to that, with just omitting some maybe unnecessary details. So here we have the BSC class, or binary search class, which is a generic class, which means that the type of the data for each node will be specified later. So the binary search tree, the main or the most important variable is the root, and the class node has the data for each node, and the left child and the right child also. We can keep track of the parent node, which one is the parent, just to do the things faster. Here we see the search method with passing a key k, and as you see here, it calls another search method which has two parameters, the key k and also the root node of the tree. So this search method here is actually a recursive method here. As you see, it calls itself twice, depending on which condition is true inside the method. So we're checking if n is equal to null and n is the node. We're trying to compare its data with versus the key k. If the node n is null, means that the search was unsuccessful. So here it's the a case of unsuccessful search. So unsuccessful search. If the data we're looking for is at the data, or is the data of like the node n, then we're done. So that's the successful search. So that's a successful search. Otherwise, if the data of like the node n is smaller than the key k, then we need to search the right side. So here we're assuming that again k, the value we're looking for, has a higher value compared to the data, means that we need to search the right side. So here is searching the right side, or the right subtree. And otherwise, if the data we're looking for is less than the data of the node n, means that we need to search the left subtree. Okay, so here again, we're not worried about this inequality sign here. In actual code, we might need to use actually maybe a compare method or equals method, but here again we're just omitting some unnecessary details. But here we're assuming that we have implemented the proper comparison mechanism to compare the data of any type or that type E with the key that has been passed as the parameter. So let's see with k equal to 14 how this algorithm works. So first of all, we're going to start with calling the search with 14. So here change the color of the pen, so search, and 14 will be the very first thing to be called. The search 14 will call the other search method, which gonna call like the pass the root as well to the search. So that means that the root will be the node n in this search method that we have here. When in this case, the root is actually the node 10. So n is 10. So the node n is 10, or the data of like the node n is 10. So because 14 has a higher value compared to 10, it means that we're going to call this one, which is search the right side of the tree. So this one call, because here we're going to say 14 is greater than 10, it's going to call the search method, again passing the 14, but the right child of the node n. So I'm going to write n dot like it's gonna be the right child of 10, which is 15. And again, this is the n dot right. So n dot right will be search. So going to the code again one more time. So it's a recursive call again, and n is not null for sure because it has a value 15, and the data of the node n, which is 15, is not equal to 14. And as we see here, this time the value of k, which is 14, is less than the data of like the node n. So this time we're gonna go and call this one with the left child of the node n, and again, and here is 15. So here, because 15 is greater than 10, or let's write it this way just to be consistent. So because 14 is less than 15, so we're gonna call the search method passing the 14, but this time the left child of 15, which is 12. So, and here is gonna be n dot left. So n dot left is passed. Now, so 12 is the number. Again, going to the search method, again, is a recursive one. The data is not equal, is not the data is not null, so we're good. And we see that the k here is greater than the data of the node, which means that again we're going to go to this call here. I'm going to write here, because 14 is greater than 12, we're going to call the search method, again passing the 14, but this time is going to be the right child of 12, which is 14. So 14, and this is actually, again, it is n dot right. So here, let's go and let's see what happens. Here n is not equal to null, but as you see this time, n that data is equal to k. So this time this will be the case, and we're going to return n. So this will return, let's just use the color black here. So it's going to be going to return the node n, which again contains the data 14. So just for the sake of simplicity, we are using like the numeric data types for our nodes, but again, it can be any kind of like the data, as long as we have implemented a proper comparison mechanism for comparing the data of each node to another one, or with the key, we should be able to implement the search method easily. So as you see, the search operation or the search method can return, it can be either successful or unsuccessful depending on if the data exists in the tree or not. So you might ask about the time complexity of the search operation. For sure, as you see, it depends on how many times we need to recall or call the search method again, recursively. It depends on the height of the tree, as I discussed just a few minutes ago, that it all depends or is from the big O of h, and depending on in the worst case is from the big O of h, means that it can go up to the down to the very deepest part of the tree at the worst case. In the best case, it's really easy to see that the best case will be big O of 1, because for example, if k is equal to 10, the very first search will return number 10. So it is there. And in average, again, depending on the structure of the tree, that's very important that what can be the structure of the tree. We might have like something like the logarithm of n, which is and n is the number of nodes that we have inside the tree. So the h in the binary search tree, h can be a number from can be very close to n, or it can be so I'm going to write here between n and almost between the logarithm of n in the base 2. So depending on the again the structure of the tree, the big O of in the worst case we might have like the big O of n or big O of logarithm of n in the base 2. But so that's why I just wrote the big of age. Again, just saying that the worst cases can be, it depends on the age. But in watch my other videos that I went over the binary search trees, time complexity of the search operation, and then explained that in more details with several many other examples of that. So that's the search method, but for sure we need to implement some other methods such as the the insert method. So it's really easy to see that the insert method is actually the result of an unsuccessful search, because when we're going to insert an item which does not exist in the tree, so the result of unsuccessful search will lead to an insert. And the delete operation, we're assuming that the node exists, means that the search was successful, so we can delete the node. So I'm going to just also talk about the insertion operation in a tree. Now we're taking a look at the insert method of the binary search tree. As I said, the insert is the result of an unsuccessful search, and that's how what we need to implement. In this video, I have used an iterative approach to implement the insert method, but for sure we can write also a recursive approach that will be discussed in another video. For this video, we're going to use this iterative version. So assuming that we are going to insert the node Q with some data, for this method we're keeping two nodes, the current node and the parent of the current node. And the reason that we need to keep the parent of the current node, because if the current node is null, which means that the search was unsuccessful, we need to insert the node Q to be either the left child or the right child of the node P. And I'm going to explain with this example that we hear that how it works. So let's say that we're going to insert number 16 in this tree. Again, we're assuming that we're dealing with numeric data, but the type E can be anything, and we might need to implement the equals or compare to methods to be able to compare the data of the nodes of type E. So at the very beginning of insertion method, we have the numbers like the C and B. So I'm going to write here insert. Actually, let me use the a better ink here. So we're calling insert, and let's say we are going to insert 16. And again, the node that contains the value 16. So here we're gonna see C to be the root, which is the node 10, and we're gonna see that the parent will be equal to null, which is the parent of the node like the root, which is 10. So here I forgot to actually add something. If the root C is also or the node C is also null, means that the tree is empty, then the Q will be the root. So maybe I need to add this one, that if C is equal to null, then we're going to just simply say root is equal to Q, and this the while loop will go to the else part. So else, and then we have this giant while loop structure here. After adding this if statement and the else statement, here we're going to start with like this C equal to 10 and P equal to null. This is the parent of the root. And then it says while the C is not null, and we're going to put the C to be a parent, parent to be the C. So immediately after the this while loop, we're going to set P to equal to 10, and now that's what we're going to do. We're going to say if the data of the current node is greater than or equal to the data of the new node we're going to insert, or is less than that. And because 16 has a higher value compared to 10, which it means that the current node will be the right node of the current. So here we're going to update C to be C dot right, which going to be equal to 10 dot right. which gonna be 15. So going back to the while loop again here, so it goes back here, and because C is not null yet, means that the search is still continues. We're gonna put the P to be the current node, or the C, which gonna be 15. It means that if here the search is unsuccessful and there's no left or right child for the node 15, 15 will be the parent node of the node Q. So that's what we need to keep the node P. So here we're comparing the data of the node C with Q, because 16 is still greater than 15. We'll update C to be the C.right, which is gonna be 15.right, which is gonna be 18. And goes back to the while loop again here, and we're updating the parent to be C, which is going to be the node 18. Again, if the search is unsuccessful, which we're going to see this is the case now, we're going to put the parent node to be 18. So here P is 18, and so the C is still 18, and we're comparing the value of 18 and 16, and because 16 is less than 18, the current node will be the left child of, so C will be C.left, or in other word 18.left, which in this case is null. If you look at this example here, this node on the left side does not exist, so nothing's here, and that means that we need to insert the the new node. So it goes to the while loop, and because now the current node is null, so the current node becomes null, and it goes out of the while loop, and as you see here, still the node P is equal to 18, which is the node that we're going to insert the node in. So we're going to do one more if statement here, which is if the data of the C, which is actually I need just to see here is P not also the P, so it's P and here. So if the data of the parent node is greater than Q, which is the case, we're going to put the left child of the parent to be the Q. So that's the very last step, that we're going to put P.left to be the node Q. So which means that because P is the node that contains 18, so we're going to insert the new node here, and I'm going to use the other color with the node with the data 16 here to the very left of the node 18. So again, if the root is empty, we need to add this one. So again, I'm just going to emphasize this one. So if C is equal to null, means that the tree is empty. We just simply put the root to be the node Q. Otherwise, we need to just do a search, which will be an unsuccessful search, which will lead to where we need to insert this node that we have.